Hello, welcome to the Zero at Work Gas Day. We will talk about gas networks and how to optimize them. I will spare you the European regulations, but give you an introduction into the basics, talk a very little bit about network design, and then mostly about how to compute capacity and how to control a network. Here you can see the energy team. Tom, Janina, Mark, Kai, Christine, Charlie, Carsten, Jaap, Jan, Inchi, Lovis, Tai, Milena, Niels, Felix, and Ying. You will see them again today in some of the lectures and also in the exercises. But now let us start.
Natural gas consists mostly of methane, though depending on the source it can contain also some other hydrocarbons or some nitrogen or some carbon dioxide. LNG is just liquefied natural gas. In contrast, LPG is liquefied petroleum gas and consists mostly of higher hydrocarbons like propane and butane. Let us imagine we have a place where gas is produced and another place where it can be consumed. Then we can build a pipeline to connect both. Now to get the gas moving, we have to apply pressure, or more precisely, we need a pressure difference between the entry and the exit. So if we put the gas here at the entry with say 50 bar in, it will expand towards the exit and lose pressure on the way. Therefore, the pressure at the exit might be only 30 bar. Obviously, this is in a dynamic process, as once the gas leaves the pipeline, the pressure also at the entry will drop unless new gas is coming in. There's also a loss of pressure due to friction in the pipeline. This can all be nicely described by an Euler equation you can see here, which has some continuity equation, a momentum equation, and some energy conservation. Please note that a change in the pressure proliferates much faster to the pipeline than the gas itself. Now if we assume a stationary condition and lots of other things and close both eyes, we can simplify it to what you see here, which is called the Weymouth equation. And the alpha basically has everything in it. So about the dimension and inclination of the pipeline, the friction, gas temperature, gas composition, outside temperature, and whatever you find there, it's all kind of put into this alpha. And still then, I mean, this is a simplification which is only true in the stationary case. Now let us build a network. Let us assume 2 entries and 4 exits like this here. You have to understand this is all coupled through pressure. So the input pressure at the entries is given, so it proliferates through the network. Let us assume for the moment that the amount of gas entering and leaving is balanced. Then we can compute the pressure at the exits. Now we change the pressure at any outside point, the whole network changes. So it's all coupled. And there is a distinct equilibrium, and this is called the line theorem, which I will show you. Here you see the line theorem, and basically given a balanced demand and a strictly increasing function, then the solution space of Q and pi in this case squared pressures, is subject to the following conditions, is either empty or fulfills these conditions. The flow is unique, and the squared pressure component pi has this form, which basically says that it's kind of a line which is given. So in the result, the flow is unique, given that phi is strictly increasing, and the pressure differences or the differences of the squared pressures are uniquely determined for all the arcs. So shifting all values by a constant is feasible. A constant shift is the only possible source of a difference. So consider 2 feasible squared pressure vectors, pi tick and pi 2 tick. Both are shifted in such a way that they are coincident in the value at u. Then the difference is constant, which implies that they're basically the same. We can reformulate the problem by adding some slacks, and this way we basically can ensure that the solution space is always non-empty, and we have a convex problem now here, which is kind of nice. So basically it says that if we have a passive network, we can solve a passive stationary network, we can solve the problem to compute the pressures with a convex optimization. It's a convex optimization problem. Now we want a network that we can actually control. So apart from the pipelines to connect things, we have 3 active elements. We have valves, which allow us to switch something on and off, basically have the pipeline connected or not connected. Then we have a regulator, which allows us to decrease pressure. And we have a compressor, which allows us to increase pressure. And with these three elements, we basically can achieve whatever we want. The pictures you see, there's a compressor machine and a valve. So here you see an example of a controllable network, which is just one compressor station, but you see there are a lot of compressor machines, a lot of valves, some regulators, and this together is basically then a real network. So actually the most difficult element are the compressor machines. And they are important because they increase the pressure and basically are responsible for pushing the gas through the network. But the problem is that the output or the performance of the compressor machine depends on the input pressure, the output pressure, the flow, the temperature, the composition, and pretty much everything else. Most important being the compressor power, because there's a power source at the compressor, and depending on the power and the other parameters, there's a certain amount of pressure difference you can achieve. And of course, if you have several compressors, it gets even more interesting. As you can see here, you can put them in parallel or in serial, and that way get one performance or the other. I mean, if you have parallel, you can get more flow through the machines. If you have them in serial, you can have a higher compression ratio, and so on. And to make it more interesting, actually even the outside air temperature has a lot of influence. So if you have just 10 degrees difference, you get another 3% more power, and this might be then allow you to put some more megawatts of gas through your compressor machine. One thing to keep in mind is that it's basically there is no description for each compressor machine which precisely says what this machine can do. I mean, they have been built sometimes decades ago, and situation changes, and therefore you only have a rough estimate of what it can do. This being said, if you have such a gas network, there are three basic questions you can ask from an optimization point of view. One is how to design a new network or extend an existing one. The other is, given a network, determine the capacity of that network, which, as I explained, is a bit difficult. And finally, given a network, control the network to achieve maximum efficiency. On all the 3 points, there will be some more introduction from me, and then later on you get a detailed introduction by my colleagues. Let me slowly talk about network design. So how to design a new network. This is just a teaser. I just give you 2 keywords, and then you have to do on your own, because it's a huge topic, and with a wealth of stuff is just out of question here. Here's these 3 nodes. And now we want to connect these 3 nodes with the minimum amount of pipeline possible. I mean, as I said, it's expensive. This is kind of important. And what you do is you build a node in the middle between these 3 points and connect it. This problem is known as the Steiner tree problem, and is a very old problem in mathematics. Now, in reality, usually you're not free to put your intermediate node wherever you want. I mean, there might be just a city or a building or environment protection place or whatever, and so there are only kind of discrete choices here. So what you do is basically you build a network with all the possible choices, and now look for the intermediate nodes you need to connect the kind of outer nodes you want to have. And this is called the Steiner tree problem in graphs. The outer nodes are called terminals here, and the problem is, as you can see here, given an undirected connected graph and some costs on the edges, find a set of intermediate nodes such that the whole graph gets connected at minimum cost. And this is actually one of the classical 21 NP-hard problems. It's kind of a lot of similarities to the traveling salesman problem, and there is really a lot of literature about this. Here you see just one possible formulation format, which is the direct cut formula, integer programming formulation. Actually, it's for the Steiner arbitrary sense problem, but by just bidirecting all the arcs and choosing an arbitrary node as root, this also solves the Steiner tree problem. You have variables y for the arcs, which you want to minimize, and then you basically say, okay, now from every cut we have in the graph, there has to be at least one arc going over the cut, provided that the root is in one part of the cut and some terminal is in the other part. So if you're interested in this stuff, there is SkipCheck, which is a solver for Steiner tree problems and graphs, and it's now part of the skip optimization suite. And the point is that the Steiner tree problem as a traveling salesman problem hardly ever is found in pure form in the wild. So normally there are some extra restrictions or conditions, like you have node weights, or you have it's rooted, or you have a group Steiner tree problem where you only have to connect one out of a set of nodes and so on, or you have some hop constraints and so on. And actually SkipCheck can solve 11 of these varieties, and if you have these kind of problems, give it a try. You can just download the stuff, and I can say we made a lot of progress there. It's like everything, once you start to dig into some problem and to work on it, you make more and more progress. So for example, for the rooted price collecting Steiner tree problem, there was a Dymex competition. The first publication about this by Lubitsch in 2004 took for some instances 4,000 seconds. At the Dymex competition we were down to 100, and by now we can actually solve it in less than a second. So these problems can be solved to quite some size, to optimality. On the other hand, there are also some which are incredibly hard.